Okay, welcome to part one of our lecture video series for Wednesday, April 26th, where we discuss what we call the heat of reaction, really specifically the enthalpy of reaction, delta H reaction. So to remind ourselves about why it is that we are using kind of this language of heat and enthalpy interchangeably, remember, as long as we are at constant pressure, the mathematical definitions of total internal energy and enthalpy allow us to say that the enthalpy change of some process is equal to the heat that is either lost or gained by our system as long as we're at constant pressure. So it's kind of the main condition that allows us to say that enthalpy and heat, Q, are the same. So again, Q sub P, this is the amount of heat that is either lost or gained by our system as long as our system is at constant pressure. And most of, remember, our chemical reactions done in the lab are, right? We are not typically restraining our volume to be constant. Rather, we do our reactions kind of out in the open under constant atmospheric pressure. And in this class, at this level, we kind of ignore any kind of micro fluctuations that might result as a result of different like barometric pressures throughout the day or in the lab. But in general, what you need to know is that delta H is equal to Q at constant pressure. So this is where that language of heat comes from, right? We can say that the change in enthalpy for some system is equal to the heat that is absorbed or lost by that system, as long as we're at constant pressure. See our lecture video on Monday where we kind of go through the math of where this comes from if you need a little bit of a reminder. So then why is it that I am introducing this new thing called heat of reaction when we've already kind of looked at heat exchanged as the result of some kind of chemical process, or at least looking at the heat exchange between objects? So let's talk about it. Start with a definition, define. Let's define the heat of reaction. Delta H subreaction. So this is known as the change in the total heat of a system, specifically that system being a chemical reaction, as the result of some chemical reaction. So we could say this a couple of different ways. Mathematically, we could say that the heat of reaction is equal to the enthalpy of our products so the total heat in our product system minus the enthalpy of our reactants, or the total heat in our reactant system. And when we're talking about the heat of reaction, the thing that makes it kind of distinct from just like a normal enthalpy calculation is this is always expressed in the amount of heat that is either absorbed or released per mole of either reactant, but typically more often it's per mole of product. So that means that our unit, if we're talking about a heat that is absorbed or released per mole, the unit is then going to be joules per mole. Or if we absorb or release larger amounts of energy, could even be kilojoules per mole. And we'll probably almost actually see kilojoules per mole a little bit more than joules per mole. But yeah, what you need to know is that heat of reaction is the change in the total heat of a system as a result of some chemical reaction, namely the difference in the heat of the system in the product's form compared to the total heat in the system in the reactants form, and is expressed always per mole of some reacting species, typically actually per mole of product. So let's think about the ways in which our enthalpy of our product and reactants can change. So 2 ways in which the heat of our reactant system can change. So what I'm going to do is I'm going to sketch a couple of diagrams where on the x-axis we're going to look at the passage of time. So this is reaction time. So once the reaction starts, what's going on? And then here on the y-axis, I am going to look at kind of a generic energy axis. And when we keep talking about this later, you will understand why it is that I'm using a generic energy axis. But in general, let's look at the 2 different ways that a reaction can kind of exchange heat with its surroundings. So let's suppose that we have some reactants at some initial energy state over here. So we could call this the total heat of the reactant system. And let's call our reactants A coming together with B. Now let's suppose that in order for this reaction to happen, energy is required. So energy is going to be pumped into the system or absorbed by our reactants in order for our products. Nope, that's not what I wanted. To be formed. So over here, is the heat of the products, or the enthalpy of the product state. Let's call it a synthesis, AB. If we were to find our heat of reaction, which is again the difference between our product state, which here I'm going to go ahead and be specific, minus the enthalpy or heat of our reactant state, we would see that since we wound up at a higher energy state as a result of our products being formed compared to when we had our reactants just sitting around in our beaker, if it's an aqueous reaction, then the difference in these energy states is the heat of reaction. And specifically, in order for us to get from reactants to products, we had to increase the amount of energy that our reactants had available to us. So this is a positive heat of reaction. And remember, this positive sign means that we've got energy, and if we're talking about enthalpy here, this means that we've got heat that is being absorbed. So in order for the reaction to happen, our system had to absorb heat from the surroundings. And we call this kind of process an endothermic reaction. So endo, meaning like internal, you can think about, if you've heard of any kind of like neurochemistry, neurobiology, you have things called endogenous neurotransmitters. So that means that they're like already present in your brain, within your brain, endo. If you want to think about an endoskeleton as opposed to an exoskeleton, human beings have endoskeletons, thankfully, yay. Be pretty horrific if we didn't. And again, endothermic means that our system absorbs heat from the surroundings. So let's do a comparison then about the opposite scenario. So what if, over the course of our reaction runtime, we started at some initial reactant state. Let's look at, I don't know, how about the exact inverse of this reaction? So let's look at the decomposition of AB. So this is our reactants. And as time progressed, we saw that our system went from a higher energy state to a lower energy state to form products, such that our product enthalpy is lower than the initial. So let's write that out mathematically. If I were to try to figure out the heat or enthalpy of reaction, this would be the heat of our product state, which is A plus B, minus the heat of our reactant state, which is AB. So if I'm looking here at the heat of my reactant state, I would see that my enthalpy dropped. And because I saw this difference where I went from a high energy state to a low energy state, I am getting rid of energy, which means I have to be releasing it outward away from my system. So negative heat of reaction. Where again, a negative sign means that we're talking about a release. And since we're talking about a heat of reaction, then we're talking about heat being released as a result of this chemical reaction. So since heat is being released from the system into the surroundings, outward away, we call this an exothermic reaction. Now let's talk a little bit about the consequences of kind of like what we would feel if we were to observe endo and exothermic reactions in the lab. So let's think about what we might actually perceive as a result of each of these processes. So let's see here. Let's say we've got a reaction where we've got our, oh boy, can I draw a beaker today? Let's see. Where we've got reactants going to products. And let's suppose this is an aqueous solution. Why not? Aqueous reaction. All right, so I've got particles A and B in solution that are coming together to form AB. And if this is an endothermic process, that means that heat needs to be absorbed into the system, inside the system, endo. So heat is going to be absorbed into the system, and the only way it can get heat is by absorbing it from the surroundings, right? It's not just going to pull heat out of nowhere. That would break the rules of physics. So we see here that heat is absorbed from the surroundings. Now, if you and I are going to pick up and actually handle this particular beaker and try to feel what's going on with the temperature change of results of heat being exchanged between system and surroundings, Let's think about what you and I would actually perceive. So remember, if we were to hold on to this beaker, we would not be part of the chemical system because we are not reactant particles A, B, or product particles A, B. Rather, we're part of the surroundings. So if we were holding on to this beaker as the reaction were happening, the heat of the surroundings that is being drawn upon would include the heat that we have in our hand. So what would we feel if heat is being transferred away from us? We would feel, since we are part of the surroundings, the heat transfer being away from us, and if something loses heat, we perceive that as a cooling. Because again, we're part of the surroundings. Now, what about if we were an exothermic reaction? So here looking at the inverse of kind of our endothermic. So this is where we start with reactant AB, which then decomposes into components A and components B. All right, if this is exothermic, then that means that heat is being released out of our system. So let's make that statement here. Heat is released to the surroundings. So then if you and I, part of the surroundings, were to feel this beaker, what would we perceive? We would feel heat. We would feel temperature increase. So this might seem really intuitive to you, and good, it should. I would hope so. But in general, people think like endothermic with the positive and exothermic with the negative. Like we think like exothermic as like generating, we think about like endothermic like negative, meaning like a release or loss. And it's true from the perspective of the system, right? The system itself in an exothermic reaction, which has that negative sign, right, is losing heat to the surroundings. So the system itself is going to be cooler, right? That's the system. But since you and I are not part of those reactant and product molecules, we're part of the surroundings, we're going to feel that heat that's being transferred out of the system into the surroundings. So we feel an increase in temperature. So this is why I said a couple videos ago that it's a really good idea to try to familiarize yourself with what the system is and what the surroundings are and be super explicit about those definitions, because that way you won't get mixed up with kind of thinking about where energy now, especially when our conversation is shifted to enthalpy, heat is being transferred to or from. From what to what? What's the system? What's the surroundings? So this is the heat of a reaction. In our next video, we are going to practice this idea a little bit more. So we are going to look at how we can take some experimental data, so things we can measure directly in the lab, and use that to determine the amount of heat that is exchanged or changed as a result of some reactant system going to products. And then we'll talk about how we can figure out the heat of reaction theoretically. So up next, determining the heat of reaction empirically, and as you might be able to predict, that is going to involve, yet again, calorimetry.